When we step outside on a clear night and look up, the sky can seem endless, stars scattered across the darkness, silent and remote. But if you look carefully, especially far from the lights of cities, you'll notice something different. A faint glowing band stretching across the heavens. Ancient cultures gave it names, weaving myths about a river of milk, a celestial pathway, or the spine of the night sky. Today we call it the Milky Way. That hazy band isn't a cloud or a trick of the atmosphere. It's the combined light of billions of stars, so many and so distant that their glow blurs together into a river of starlight. What we see from Earth is just a thin slice of something far greater, the galaxy that is our home. The Milky Way is vast beyond imagination. A rotating disk more than 100,000 light-years across, containing hundreds of billions of stars, countless planets, and an unknown amount of dark matter that we can't see but know must be there. Every star you've ever observed with the naked eye, every constellation, every meteor shower we've watched streak across the night, all of it exists within this one immense system. And somewhere inside that system, on a small arm of the galaxy, orbiting an ordinary star, sits our solar system and our planet Earth. We are inhabitants of this enormous structure, passengers carried along by the gravity and motion of the Milky Way itself. But what exactly is this galaxy? How is it built? What secrets does it hold about the origin of stars, the birth of worlds, and the conditions that made life possible here? At the center of the Milky Way lies a supermassive black hole, a gravitational monster with millions of times the mass of our Sun. Surrounding us are dozens of smaller companion galaxies, neighbors and satellites that orbit our home like distant relatives. And stretched across its spiraling arms are the nurseries of stars, where new suns and new worlds are still being born. To understand our place in the universe, we must first understand the Milky Way. Because the story of this galaxy is, in a very real sense, the story of us. The stars forged the elements that make up our bodies. The spiral arms shaped the clouds that became our solar system. And the history of this galaxy continues to unfold around us, guiding our future. So as we begin this journey into the Milky Way, we'll ask some of the biggest questions. Where exactly are we within this vast system? How do astronomers map something so enormous when we're trapped inside it? And what does the structure of our home galaxy tell us about the universe as a whole? This is the Milky Way, our galaxy, our home, and our window into the cosmos. To understand the Milky Way, we first need to step back and think about what a galaxy really is. At its core, a galaxy is a massive system of stars, gas, dust, and dark matter, all bound together by gravity. But not all galaxies are the same. Some are elliptical, shaped like footballs of stars. Others are irregular, with no clear form. Our home galaxy, the Milky Way, is a barred spiral, a majestic structure with sweeping arms that curl outward from a dense center. But here's the challenge. We live inside this galaxy. It's like trying to draw a map of your own city while never leaving your street. We can't step outside and take a photograph of the Milky Way from above. Instead, astronomers piece together its structure from within, using careful observations, star surveys, and measurements of gas and dust. What they've uncovered is a galaxy that can be divided into 4 major parts: the disk, the spiral arms, the central bulge, and the halo. Let's begin with the disk. The disk is the most obvious and familiar part of the Milky Way because it's where our own sun resides. Imagine a giant rotating pancake of stars and gas, about 100,000 light-years across, but only a few thousand light-years thick. This thin, flat plane is where most of the galaxy's stars, including ours, live. When we look at the Milky Way in the night sky, that glowing band across the heavens, what we're really seeing is the disk, billions of stars packed along our line of sight, smeared together into a glowing river. But the disk isn't uniform. It's structured into spiral arms, vast lanes of stars, gas and dust that wind their way around the galaxy. These aren't rigid structures like the arms of a pinwheel. They're more like waves, regions where material becomes compressed, sparking new star formation. Picture cars on a highway during rush hour. The traffic jam itself moves slowly along the road, while individual cars come and go. The spiral arms work the same way. Stars move in and out of them, but the pattern persists. Our galaxy has several major arms. The Perseus arm stretches outward, rich with star-forming regions. The Sagittarius arm cuts closer to the center, filled with clusters of hot young stars. And then there's the Orion spur, our neighborhood. The Sun, Earth, and the entire solar system sit here, a minor branch between the larger Perseus and Sagittarius arms. It's humbling to think of our position, not at the center of the galaxy, not in one of the grand arms, but on a small spur, a quiet back road in the vast city of the Milky Way. At the heart of the galaxy lies the bulge. If the disk is the pancake, the bulge is the yolk of the egg, dense, compact, and filled with some of the oldest stars in the galaxy. This region is a crowded metropolis compared to the suburbs of the spiral arms. Stars here orbit in all directions, not in the organized rotation of the disk. The bulge is also home to the galaxy's most mysterious resident, the supermassive black hole, Sagittarius A star. Though invisible, its immense gravity shapes the motion of stars at the very center. Surrounding all of this is the halo, a vast, faint sphere of stars and dark matter that extends far beyond the visible galaxy. The halo contains globular clusters, which are tight, spherical swarms of ancient stars. Some of these clusters are over 12 billion years old, nearly as old as the universe itself, relics from the Milky Way's earliest days. But the halo also holds something we can't see: dark matter. Astronomers know it must be there because the stars in the disk rotate faster than they should if only visible matter were present. Something unseen, outweighing everything we can see, is holding the galaxy together. That something is dark matter, and most of it lies in the halo. So how do we piece all this together from inside? That's where modern astronomy steps in. Missions like the Gaia spacecraft map the precise positions and motions of more than 1 billion stars, giving us a 3D view of our surroundings. Large surveys like the Sloan Digital Sky Survey scan the sky and capture the light of millions of objects, allowing us to trace the arms, measure the bulge, and even glimpse faint halo stars. Through this detective work, we build a map, not perfect, but detailed enough to reveal the Milky Way's grand architecture. To put it all together, think of the Milky Way like a cosmic fried egg. The disk is the flat white, thin but broad, spinning around the center. The bulge is the yolk, dense and bright. The spiral arms are streaks of color painted across the white, swirling patterns that give the galaxy its character. And the halo, that's the invisible plate beneath it all, holding everything in place even if we can't quite see it. This structure isn't static, it's dynamic, alive and changing. Stars orbit, spiral arms wind, the bulge stirs, and the halo stretches beyond our reach. And through it all, we drift along with the sun, orbiting the center once every 230 million years. Right now, we're just passengers on one journey around the galactic core, a journey we've made less than 20 times since the Earth was born. Understanding the shape and structure of the Milky Way isn't just about mapping where the stars are. It's about understanding the stage on which cosmic history unfolds. The disk is where new stars are born. The bulge is a fossil record of the early galaxy. The halo holds clues about dark matter and ancient mergers. And the spiral arms, including our humble Orion spur, are where the drama of stellar life and death plays out. From the thin disk to the dark halo, the Milky Way is both familiar and mysterious. A galaxy we know intimately because it's home, yet one we're still learning to chart, piece by piece, from the inside looking out. Now that we've explored the overall structure of the Milky Way, let's turn to the real heart of the galaxy, the stars themselves. Because when we talk about galaxies, we're really talking about vast collections of stars, born, living and dying across billions of years. But stars don't simply appear out of nowhere. They're born in some of the most spectacular regions of the galaxy, nebulae and molecular clouds. Nebulae are vast clouds of gas and dust, sometimes stretching across dozens or even hundreds of light years. Within these clouds are denser regions called molecular clouds, where the conditions are just right for gravity to take over. Imagine a giant fog, but instead of water droplets, it's made of hydrogen molecules. Over time, pockets of gas collapse under their own weight, growing hotter and denser until the pressure ignites nuclear fusion. That's the birth of a star. These stellar nurseries are scattered throughout the spiral arms of the Milky Way. That's no coincidence. The spiral arms are like waves of compression, gathering gas and dust as they sweep around the disk. As the material piles up, it triggers new generations of stars. If you could see the galaxy from the outside, the spiral arms would glow with clusters of brilliant young stars, evidence of the ongoing cycle of star formation. And those newborn stars, they're hot, massive, and short-lived. Many shine with a blue-white brilliance, far brighter than our sun. But they burn through their fuel quickly, living only millions of years before collapsing or exploding. These young blue stars light up the nebulae around them, sculpting the gas into spectacular shapes. Some of the most famous images from telescopes, the Pillars of Creation, the Orion Nebula, are glimpses of this process in action, snapshots of stellar birth. Contrast this with the older populations of stars in the galaxy. In the central bulge and the halo, you find red giants and ancient stars that formed billions of years ago. These stars are cooler, dimmer, and often carry fewer heavy elements. In fact, astronomers can tell a star's age by its composition. The earliest stars in the galaxy contained almost nothing but hydrogen and helium, the raw ingredients from the Big Bang. As stars lived and died, they forged heavier elements in their cores and through their explosions, enriching the galaxy over time. This process is known as chemical evolution. Each generation of stars adds to the mix, seeding the galaxy with carbon, oxygen, iron, and countless other elements. When a massive star dies in a supernova, it scatters those elements into space, where they mix with gas clouds and eventually form new stars, new planets, and even new life. Our Sun is a second or third generation star. It contains elements heavier than hydrogen and helium, what astronomers call metals. And it's those metals that made Earth possible. The iron in our blood, the calcium in our bones, the oxygen we breathe, all of it was forged in the hearts of ancient stars and spread across the galaxy by their deaths. It's no exaggeration to say that we are made of stardust. Every atom heavier than helium inside your body was once part of a star that lived and died long before our solar system existed. When you look up at the night sky, you're not just seeing distant suns. You're seeing the factories that built the ingredients of life itself. This ongoing cycle, birth, life, death, and rebirth, is the heartbeat of the Milky Way. The spiral arms are like nurseries, glowing with the light of young blue stars. The bulge and halo are more like retirement homes, filled with ancient red giants nearing the ends of their lives. And in between lies the constant recycling of material, turning gas into stars, stars into heavy elements, and heavy elements into new worlds. Astronomers study this cycle not just to understand stars, but to understand the galaxy as a whole. By tracing the chemical fingerprints of stars, measuring the abundance of elements like carbon, oxygen, or iron, they can map how the Milky Way has grown and evolved over billions of years. They can even identify stars that originated in smaller galaxies, long ago consumed by the Milky Way because their chemistry doesn't match the stars around them. So when we talk about the stars of the Milky Way, we're not just cataloging points of light, we're tracing a cosmic story that stretches back nearly to the birth of the universe. A story where each generation builds on the last, enriching the galaxy and setting the stage for new possibilities. And ultimately, it's a story that connects directly to us. Without billions of years of star formation and chemical evolution, Earth would never have existed, and neither would life. The stars are not just out there in the night sky. They are within us, their atoms living on in our bodies. As the physicist Carl Sagan once said, "We are a way for the cosmos to know itself." In the Milky Way, that's literally true. The galaxy gave us the raw materials, and through us, it has gained the ability to look back, to reflect, and to ask questions about its own origin. At the very heart of the Milky Way lies an object of immense mystery and power, a supermassive black hole named Sagittarius, a star. Unlike ordinary black holes, which form from the collapse of a single massive star, supermassive black holes contain millions, sometimes billions, of times the mass of our Sun. Sagittarius A star alone weighs in at roughly 4 million solar masses. It sits quietly at the galactic center, surrounded by dense clouds of stars and gas, a gravitational anchor around which the entire Milky Way revolves. Black holes are famously invisible, and Sagittarius A star is no exception. Its gravity is so strong that not even light can escape once it passes the event horizon, the point of no return. But while we cannot see the black hole itself, we can observe its effects on the surrounding stars. For decades, astronomers have tracked stars in tight orbits around the center of the galaxy, and their rapid elliptical paths reveal the presence of an incredibly compact and massive object, the unmistakable signature of a supermassive black hole. These observations were groundbreaking. In 2020, the Nobel Prize in Physics was awarded for studies of these stellar orbits, confirming with extraordinary precision the existence of Sagittarius A star. By watching the motion of stars over years and decades, scientists can calculate the black hole's mass and even learn about the shape of space-time in its immediate vicinity. But what exactly is a black hole, and why does it form? A black hole is a region of space where gravity overwhelms all other forces. Normally, a star maintains a balance between the inward pull of gravity and the outward push of pressure from nuclear fusion in its core. If a mass becomes concentrated enough, gravity wins completely, collapsing the matter into an infinitely dense point called a singularity. Around this singularity is the event horizon, the invisible boundary beyond which nothing can escape. Sagittarius A star is not the only black hole in the galaxy. Stellar mass black holes are scattered throughout the Milky Way, but it is by far the largest, the dominant gravitational player at the center. It anchors the bulge and inner disk, and even though it appears calm today, its history is likely violent. It may have grown by consuming gas, stars, or even other black holes during the galaxy's evolution. Despite its tremendous mass, Sagittarius A star is relatively quiet compared to some supermassive black holes in other galaxies. Many black holes actively feed on gas and dust, producing enormous jets of energy and X-rays. Our black hole, by contrast, is modestly accreting matter. Occasionally, gas clouds or individual stars venture too close, creating small bursts of activity, but nothing on the scale of the energetic quasars seen elsewhere in the universe. The presence of Sagittarius A star is not just a curiosity, it has profound implications for the galaxy. Its gravity governs the orbits of stars near the center, helps shape the bulge, and influences the dynamics of gas and dust. Some models suggest that supermassive black holes also play a role in regulating star formation. By controlling the flow of gas in and out of the central regions, they may indirectly dictate how efficiently the galaxy can form new stars over billions of years. Studying Sagittarius A star also offers a window into some of the most extreme physics in the universe. Near the event horizon, space and time are warped in ways Einstein predicted, but few humans will ever directly experience. Temperatures soar to millions of degrees in the surrounding plasma. Magnetic fields twist and snap, generating flares of X-ray and radio emission. By observing these phenomena with telescopes on Earth and in space, astronomers can test the laws of gravity and quantum mechanics under conditions impossible to replicate in a laboratory. In recent years, the Event Horizon Telescope achieved a remarkable feat, imaging the shadow of a supermassive black hole in a distant galaxy. While Sagittarius A star is more difficult to image directly, due to its relative proximity and the motion of surrounding matter, the techniques developed are bringing us closer to seeing our own black hole's silhouette, a dark circle against a bright swirling background of hot gas. Sagittarius A star is also central to understanding the Milky Way's history. Its growth likely coincided with the formation of the galactic bulge, and it may have influenced the merging and accretion of smaller galaxies over cosmic time. By studying it, we learn not just about a single black hole, but about the life story of our galaxy as a whole. Yet for all its power and mystery, Sagittarius A star is distant, and its influence on our everyday lives is subtle. The Sun, Earth, and Solar System orbit far outside the dangerous reach of the central black hole, about 26,000 light-years away. We are safe, but the black hole's gravity quietly holds sway over the Milky Way, shaping the motion of stars, gas, and dust on a grand scale. In many ways, Sagittarius A star serves as both anchor and storyteller. It is the gravitational heart of our galaxy, a relic of the Milky Way's formation, and a laboratory for some of the most extreme phenomena in the universe. By studying it, we gain insight into the forces that govern galaxies, the life cycles of stars, and the very nature of space and time itself. Sagittarius, a star, reminds us of the vast scales and deep mysteries that exist within our galaxy. Even as we live our daily lives on a quiet spur of a spiral arm, billions of stars and a supermassive black hole continue their slow, majestic dance at the center. Understanding this black hole is not just an exercise in astrophysics, it is a way to understand the galaxy that cradles us, the cosmic environment that gave birth to our Sun, and the ancient forces that continue to shape the Milky Way today. The Milky Way is not alone. While it may dominate the night sky from our perspective, it is accompanied by a host of smaller galaxies, its satellites. These companion galaxies are far less massive than the Milky Way itself, yet they offer critical insight into the formation, evolution, and structure of our galaxy. In fact, over 50 satellite galaxies have been discovered so far, each with its own story, history, and interaction with our galaxy. The most famous of these satellites are the Large and Small Magellanic Clouds. Easily visible from the southern hemisphere, these two irregular dwarf galaxies are bright enough to be seen with the naked eye. They are close neighbors, orbiting the Milky Way and interacting gravitationally with it. Their irregular shapes hint at past tidal interactions, stretched and distorted by the Milky Way's gravity. These galaxies are rich in gas and dust, sites of active star formation, and laboratories for studying how galaxies evolve when influenced by larger neighbors. Beyond the Magellanic Clouds, there are dozens of smaller, fainter dwarf galaxies scattered around the Milky Way. Many of these are ultra-faint, nearly invisible without powerful telescopes. Galaxies like the Sagittarius Dwarf, Canis Major Dwarf, and Bootes the Y are among these satellites. Some of these dwarfs are being torn apart by the Milky Way's gravity, leaving behind streams of stars that trace their former shapes. These stellar streams are like cosmic breadcrumbs, revealing the past interactions and mergers that helped build the Milky Way's halo. Satellite galaxies are more than curiosities. They are essential to understanding the formation of our galaxy. The Milky Way, like many galaxies, grew over billions of years through the merging of smaller galaxies. Each collision or merger left behind remnants, streams of stars, globular clusters, and changes to the galactic halo. By studying the motions and compositions of these satellite galaxies, astronomers can reconstruct the history of the Milky Way's growth. Every orbit, every tidal disruption, every captured dwarf tells part of the story. The interactions between the Milky Way and its satellites are not always peaceful. Gravitational forces can stretch and distort these smaller galaxies, triggering bursts of star formation or pulling stars into long tidal streams. For example, the Sagittarius Dwarf galaxy is currently being consumed by the Milky Way, leaving a trail of stars wrapped around our galaxy like a ribbon. These interactions are slow on human timescales, but monumental on cosmic scales, spanning hundreds of millions of years. Interestingly, satellites also help us probe the invisible. Dark matter, which makes up the majority of the Milky Way's mass, cannot be seen directly. But by observing how satellite galaxies orbit and interact, astronomers can infer the distribution of dark matter within the halo. Satellites act like test particles, tracing the gravitational landscape sculpted by both visible and invisible mass. In this way, the Milky Way's companions provide insight into one of the deepest mysteries in modern astrophysics. Satellites also reveal the diversity of galactic life. Some, like the Large Magellanic Cloud, are rich in gas, actively forming stars, and chemically complex. Others, like the ultra-faint dwarfs, contain only ancient stars with few heavy elements. This contrast allows scientists to study how environment, mass, and interactions shape the evolution of galaxies. Every satellite is a window into a different chapter of cosmic history. The future of these satellites is intertwined with the fate of the Milky Way itself. Over billions of years, some will be fully absorbed, their stars becoming part of the halo or disk. Others may survive longer, orbiting as small companions for eons. And as the Milky Way moves toward its eventual collision with the Andromeda Galaxy, the gravitational dynamics of satellites will become even more complex, with some likely being ejected or reshaped by the enormous merger. From our perspective on Earth, these satellites may seem distant, faint, and unimportant. But in the grand scheme of the Milky Way, they are vital. They hold clues to the galaxy's growth, provide laboratories for understanding star formation in low-mass systems, and trace the unseen structure of dark matter. Without these companions, we would have a much less complete picture of the galaxy we call home. In many ways, the satellites remind us that even the largest structures in the universe are part of a network of relationships. The Milky Way dominates its corner of space, but it is constantly interacting with its smaller neighbors, shaping them and being shaped in return. The story of the galaxy is not just about its spiral arms, its bulge, or its black hole. It is also about these companions, orbiting silently, leaving faint trails, and silently recording the history of our galactic home. As we continue to explore the Milky Way, satellites provide an invaluable guide to its past, its present, and its future. They are evidence that galaxies are not isolated islands, but part of a cosmic ecosystem. They are living records of formation, growth, and interaction, reminders that the Milky Way, for all its size and splendor, is part of a dynamic, interconnected universe. So far, we've explored the structure of the Milky Way, its stars, its central black hole, and its satellite galaxies. But beyond the cosmic architecture and stellar phenomena lies a question that has fascinated humanity for centuries. Could life exist elsewhere in our galaxy? And if so, where? The Milky Way is not uniform in its capacity to host life. Its vast spiral arms, dense bulge, and extended halo create very different environments. Scientists have proposed the concept of the galactic habitable zone, a region where conditions may be favorable for life as we know it. In simple terms, the galactic habitable zone balances two key factors: stability and availability of elements essential for life. Near the center of the galaxy, conditions are extreme. The bulge is crowded with stars, each packed closely together. Here, supernovae, explosive deaths of massive stars, occur more frequently, bombarding the surrounding space with intense radiation. Black holes and dense star clusters make gravitational interactions more chaotic. Life, if it could arise in these regions, would have to endure an incredibly hostile environment. In contrast, the outer regions of the Milky Way are calmer but poorer in the heavy elements necessary to build planets. While these outskirts are less prone to deadly radiation, the scarcity of metals, elements like carbon, oxygen, iron, and silicon, limits the formation of rocky planets. Without these elements, worlds like Earth simply could not form. Our solar system sits in a relatively quiet neighborhood, the Orion Spur, a minor branch of the Milky Way located between the Perseus and Sagittarius arms. Here, stars are neither too crowded nor too sparse. Radiation levels are moderate, and the material needed for planet formation is abundant. This balance makes the region well suited for life, and it may not be a coincidence that Earth formed here. The galactic habitable zone is, in essence, a Goldilocks region on a galactic scale. Not too hot, not too cold, not too dense, not too sparse. But habitability is more than location. It also depends on time. The Milky Way is roughly 13.6 billion years old, and chemical evolution has played a critical role in shaping environments capable of supporting life. The first generations of stars produced only hydrogen and helium, but successive generations enriched the galaxy with heavier elements through supernova explosions. These elements, scattered across the spiral arms and incorporated into new stars and planets, are the building blocks of life. Without billions of years of stellar recycling, planets like Earth and the life they host could not exist. The search for life also leads us to exoplanets, planets orbiting stars beyond our Sun. Thousands have been discovered within the Milky Way, ranging from gas giants larger than Jupiter to rocky worlds similar to Earth. Some lie within their star's habitable zone, where liquid water could exist on the surface. Others orbit stars unlike our Sun, or exist in extreme conditions we're only beginning to understand. Each discovery expands our understanding of the potential for life, and each planet is a reminder that the Milky Way is not a static backdrop. It is a galaxy teeming with possibilities. Life in the Milky Way is also shaped by time and motion. Stars orbit the galactic center, moving through spiral arms and occasionally passing through denser regions of gas and dust. These journeys can influence the evolution of planetary systems, altering radiation exposure and potentially triggering the formation of new planetary bodies. The galaxy is a dynamic environment, and life, if it arises, must adapt to its ever-changing conditions. The Milky Way also poses profound questions about intelligent life. If the galaxy contains hundreds of billions of stars, many with potentially habitable planets, why have we not observed signs of intelligent civilizations? This is the essence of the Fermi paradox. Some scientists speculate that life may be rare, intelligence may be fleeting, or technological civilizations may self-destruct before becoming detectable. Others suggest that we simply haven't been looking long enough or in the right way. Whatever the answer, our place in the galaxy gains a new significance when we consider the possibility that we may be one of the few civilizations capable of reflecting on its own existence. Studying the Milky Way's habitability also gives insight into our own planet. Earth's environment is the product of both local and galactic-scale processes. Supernovae delivered essential elements. Spiral arm passages may have influenced climate and mass extinctions. The quiet neighborhood of the Orion Spur provided stability for life to flourish. In essence, our biology and our history are intertwined with the galaxy itself. The Milky Way is a vast ecosystem where stars, gas, dust, and planets interact over billions of years. Within this ecosystem, life emerges where conditions align, evolving alongside the galaxy's ever-changing dynamics. The spiral arms provide stellar nurseries and raw materials. The bulge and halo carry ancient stars that tell the history of the galaxy. And the galactic habitable zone, the region where our solar system resides, offers the balance needed for life to emerge and persist. In contemplating life in the Milky Way, we are not just looking outward. We are also looking inward, understanding our own origins and our place in a much larger story. Every atom in our bodies, every planet, every ocean, has a history tied to the stars. Life in the Milky Way is a reflection of the galaxy's long, complex, and ongoing journey. It is a reminder that the cosmos is not distant from us. It is within us, shaping us, and offering the possibility of connections far beyond our own world. So as we consider the stars and planets beyond our solar system, the Milky Way is not just a galaxy to be mapped or observed. It is a living, evolving system, one where life may have arisen many times, in countless forms, across the sprawling spiral arms. It is our home, our history, and perhaps our future. As we reach the end of our journey through the Milky Way, it's worth pausing to reflect on what we've discovered. From the sweeping spiral arms to the dense central bulge, from the halo of ancient stars to the hidden influence of dark matter, our galaxy is a dynamic, intricate system. Every structure, every star, every satellite galaxy tells a story of birth, evolution, and interaction over billions of years. We've explored the stellar nurseries where new stars are born, watched the life cycles of brilliant blue giants and ancient red stars, and traced the cosmic recycling that forged the elements essential for life. We've looked deep into the heart of the galaxy at Sagittarius A star, the supermassive black hole whose gravity shapes the motions of stars and gas, and observed the companions orbiting our galaxy, satellites that reveal both its history and its continuing evolution. And perhaps most profoundly, we've considered the conditions for life within the Milky Way. From the quiet stability of the Orion Spur to the galactic habitable zone, we see how our existence is intimately tied to the galaxy itself. The atoms in our bodies, the world we call home, and the very possibility of life elsewhere are all products of the Milky Way's long and complex journey. The Milky Way is more than a collection of stars. It is a living system, constantly changing, quietly shaping the destiny of billions of stars and countless planets. It is a record of the past, a stage for the present, and a guide to the future. By studying it, we gain not just knowledge of our cosmic surroundings, but a deeper understanding of ourselves, our origins, and our place in the universe. As we look up at the night sky and see that glowing river of stars stretching across the heavens, we are not just observers. We are part of the story. Each star, each arm, each distant companion galaxy is a reminder that the Milky Way is both vast and intimately connected to our own lives. The journey of understanding our galaxy is far from over. New discoveries await with every telescope, every survey, and every mission into space. And as we continue to explore, we carry with us the knowledge that the Milky Way is more than a backdrop. It is our home, our history, and our cosmic identity. This concludes our exploration of the Milky Way, our home galaxy. But the universe continues, and countless stories remain waiting among the stars. The journey is just beginning. Thank you for watching. In the next episode, we will take a closer look at another well-known galaxy in our local group, Andromeda. Please consider leaving a like and subscribing for more content like this. Also, leave in the comments ideas for videos you would like to see and what you think about our Milky Way. Take care and never stop exploring.